Welcome to the course on computational fluid dynamics. It is a course which is intended for students who are in engineering disciplines like chemical, mechanical, aerospace, civil engineering, in which fluid mechanics is very important phenomenon in the equipment and processes that they deal with. It can also be of interest to scientists, practicing engineers who need a knowledge of fluid mechanics in order to design their processes better, in order to understand the phenomena better. Now, when we come to fluid mechanics, it is a very old subject. We have known it for hundreds of years, but our knowledge of fluid mechanics is limited by the inherent complexity of the phenomena and of the equations that govern fluid motion. The equations which describe fluid motion as we use them today have been known for more than 100 years, 150 years in fact, but there is no analytical solution that is known to these equations for the general case. And what we study in our fluid mechanics courses are only for the simplest possible situations, like fully developed flow in a straight pipe and maybe some very simple one-dimensional flow cases like that. But when we look at practical applications that engineers and scientists deal with, these kind of exact solutions are totally inadequate. And when you look at how we can design them, there are a number of design correlations, but the design correlations also have a lot of limitation about these things. We will take an example of a practical fluid mechanics problem and see how inadequate our state of knowledge is in order to tackle this practical problem in a proper way. So, we will look at the specific case of a flue gas ducting in a coal power plant, coal fired thermal power plant, and this is a typical example of how fluid flow occurs in many process industry applications. What we have here is part of the gas ducting. Above this is a large duct which carries hot air, hot flue gas from the furnace, and it enters here. At the time it enters here, it is still at some 500 degrees centigrade. So, there is a lot of thermal content within this, and this needs to be exploited so that the overall efficiency of the thermal power plant is high. So, what is done is that this hot gas is sent into two heat exchangers. This one in red and this in brown are heat exchangers, and these are air preheaters. So, the hot flue gas will heat up the incoming air which is used for combustion, and thereby it exchanges some of the thermal energy which would otherwise be lost. So, in order to make this happen, the flow which is coming in through this rectangular duct of a cross section of a rectangle like this, it is a vertical pipe of this cross section, is made to turn into a 90-degree thing and then split into two streams, one going left and one going right. And this stream here is again split into two streams, one going through a primary air heater and one going through a secondary air heater. So, this goes in here, it gets cooled in the process of heating of the primary thing, and then this stream goes down here, and this stream is going into the secondary air heater, and then it comes through like this. They both mix and then they come into this, and this section will lead them into the electrostatic precipitator, ESP, and the ESP has a number of plates in which the dust which is there in the flue gas is collected by electrostatic phenomena. So, in order, the difficulty here is that you have a duct here, and this has to be fed to these battery of 4 electrostatic precipitators. These are very huge compared to these. So, that means that you will have to create space to accommodate these electrostatic precipitators. The reason why these are huge is that here the velocity can be high of the order of 10 to 15 meters per second, but for best operation inside the electrostatic precipitator you need to have something like 1 meter per second velocity, which means that the velocity has to be increased and the same flow rate has to be maintained because it is a continuous flow system, and that means that the cross sectional area of the ESP should be very high. So, these should be very large in order to maybe 10 times as large as these in order to have the same reduced velocity of 1 meter per second. So, now comes the engineering difficulty of having to distribute the flow which is coming from this into these very large equipment. So, you have to increase the size. So, this is, and you also need to accommodate 4 of them. So, that means that you take a bend here and then you come at an angle and then you split it into 4 streams here, and this stream goes into this stream goes into this, and here it goes into this. And when we are looking at a thermal power plant, it has to be operational continuously, but we also need to look at the maintenance issue. So, that is why we need to have duplication. So, the 2 are duplicated here so that you have 4 of these, and then you have an arrangement here with a gate valve. If all the 4 are working, then 2 of them will be taking the load here and 2 of them will be taking the air here. But if one of them is under maintenance, then you open the gate valve here and then you close it down here, so that all the air coming from here and here is fed through this, and then these 2 are working. So, you can have a situation where only 2 of them are working full time to remove all the dust from the flue gas, or all the 4 of them are working, and so you need to have a provision for it. So, you need to have all these provisions which will make the design very complicated in the sense that if you now try to design it, and then if you want to apply your known correlations and analytical solutions for this, you will see that it is practically impossible, because you have, if you look at it from a design point of view, you have a rectangular duct which is bringing in hot flue gas into this, and it has to take an immediate 90-degree bend, and this bend is not like the smooth kind of large radius bends that we consider. It is not an elbow of the standard type, it is of a specific type. Why is it of a specific type? Because the dimensions here are very large. This duct here can be something like 4 meters wide and 6 meters tall. Okay, so that is a huge duct, and so this can be like, this whole length can be something like 25 to 40 meters. Okay, so you are looking at such huge equipment, and these are made in terms of as rectangular walls which are erected on site, and so that means that since these are huge ducts, you do not want to carry them very long, because that will increase the cost of the initial equipment, initial cost, and it will also increase the running costs, and it will also increase the land cost, because you need to accommodate all these things in land, in public land, and land will have value. So, in practical problems you cannot honor the kind of L/D ratios that are usually required for a specific correlation to work, or for some analysis assumptions like fully developed flow to become applicable. So, you need to deal with the practical compulsions, and so you would say you take a rapid close bend here, and from here it has to split into 2. How do you split it into 2? Analytically, very difficult. It is very difficult to predict what would force the fluid which is coming from this and going through a bend, a sharp bend like this, to split evenly between these 2. And then as it is coming through this at some angle, again it has to split through this, and the flow rate through this and flow rate through this are not necessarily the same. These depend on the process requirement, how much heat you want to give to this secondary air preheater, and how much you want to give to this primary air heater. So, that means that it's not, it cannot be tackled in a simplistic way. So, and you have to take, you need to accommodate these air preheaters, and you have ducting which is bringing flow into this and separately into this, and then those are happening. Those ducting details are not shown. Okay. So, that means that you have a complicated irregular kind of piping layout in which you have flow coming in, taking sudden turns and then splitting and then further splitting equally between these two and splitting unequally between these two, going through a rotary heat exchanger, regenerative heat exchanger here, the geometry of which is very complicated, and then it comes back here and then this comes back and then they mix together and then they go through again, come up and then take a bend and then go through this angle thing, split up here, and so you can have lot of complexity which is associated with the case of single phase flow in a practical situation like the power plant. And there are constraints on your design, because if you look at the electrostatic precipitators, there are 4 of them here, and with the 2 inlets each, you would like all the 4 to be equally fed under normal operating conditions. So that means that the flow through this must be the same as the flow through this, and the flow through this must be the same as the flow through these things. They must be equal split here. And you would also like to have, despite and because of these sharp turns and then flow splits and all that, you would like to minimize the pressure drop as much as possible. So you would like to control the flow, regulate the flow despite all these singularities and obstructions that are coming here. So if you look at what can be done, is we are looking at just this ducting here, which is taking the combined flow after it goes through the 2 air preheaters and then it is fed into these ESPs. So we are looking at how to make the flow distribution even at the 4 exit points here, at the 4 exit points, despite the fact that it is coming through bend here and bend here, angled inlet and all these things. So one of the things that is often done in industry in order to reduce the pressure drop and create flow streamlining is to put some guide plates. So here you have guide plates here and guide plates here. In this bend there is a guide plate and here you have guide plates, and the idea is that you want to put these guide plates properly in order to get a good distribution. Okay, so this becomes a totally unknown kind of flow situation for which we are not equipped from a knowledge point. As engineers, we do not know where to put these things. We can use, so what engineers have developed over the years and decades is to have some thumb rules for locating these things, but how do we know that these thumb rules will apply for this particular situation with these kind of layouts, and where do you put them and how do you make this uniform? So if you look at the next thing here, you are concentrating on just this junction here, the manifold header into the ESP, and the flow is coming in like this. It should split evenly into these two, and then it should, the same amount of flow should be going through this and this, so that each ESP electrostatic precipitator is fed the same amount of dusty gas. So how do you persuade this one which is coming in at some angle to split evenly between the left side and right side, and after it turns here, how do you persuade it to go through this and this equally, because this length is shorter and this length is longer, and as it is coming through taking a bend, it already has some previous history of some inclination to go either this way or this way. So you can put guide plates here, you can put some guide plates to correct the imbalance between this flow and this flow, and then you can put some guide plates to persuade the flow to go into this and into this. On what basis do we put the guide plates? To do this experimentally would mean that we have to build this whole thing in our lab and then try various things, and they will take months and it will be very expensive. So this is what we are actually looking from for fluid mechanics. We are looking from fluid mechanics the possibility of controlling the flow in practical situations, so that we can derive the intended benefit from the process. The process can be done optimally, efficiently. Okay. Yet another example that we can consider. Let us say that we have a simple T junction, flow is coming in straight through this, and it has to split into side branch and it has to go into the straight branch. Usually the process requirement will tell us how much we want to go into the straight and how much we want to go into the branch. But what can we do as design engineers? Okay, can we design a junction here in such a way that the process, the flow which is coming in will go automatically into this and automatically into this? We cannot do that because we do not know what should be the shape. Okay, we can draw curves like this, they look very interesting curves, but how do we know that this would actually do our job? Using computational fluid dynamics, it is possible to solve the exact equations which govern the flow through this T junction. That means that it is possible to say that if this is the geometry, this is the width of the duct and length of the duct, and this is the orientation of the side branch, and this is the width of the side branch, and all these things. It is possible using CFD to solve the equations which describe the flow through this inlet, going through this outlet and going through this outlet in such a way that we can come up with a junction shape which will automatically deliver, which will direct the flow, required amount of flow into the branch outlet without having to have any valves. Okay. For example, here you have 3 different shapes. This particular junction shape here will deliver 30% of the flow into the side branch and 70% will go through the straight branch, and this one will have 50% going through the side branch, and this will go 50% here, and this will actually give us 70% going through the side branch, and this will be going only 30% will be going through this. And what are we doing here? We are creating a constriction here. We are necking this region by changing the shape of these things in such a way that more of this is going through this and less of this is going through this. In fact, if we do not have any of these controls, if we just have straight sections here, 90% of the flow would go through the straight section and only 10% would come through this. So if you want to have more flow going through the outlet, you constrain the flow, you constrict it so that you direct it to go into this. Exactly how much we have to direct and how we have to direct is something that is not known. We can make a sketch as engineers, but how do we know that it is going to be quantitatively correct? Using CFD, by solving the exact equations correctly, we can make these kind of designs possible. Okay. So that is the power of CFD. That is what we are looking from as a design engineer. This is what we would like to be doing, but this is not really possible with our simplistic flow analysis tools that were enabled in our regular engineering programs. So if you have done only 1 or 2 courses in fluid mechanics, you won't be able to tackle these realistic flow situations. But computational fluid dynamics, in which we are not looking at approximate solutions using correlations and all that, but where we are trying to solve the exact equations which govern the fluid flow, enable us to do an exact treatment of the fluid flow problem, so that we can we can hope to tackle these kind of industrial situations where you have T junctions and you have these kind of flow difficult flow situations which cannot be tackled with using conventional flow knowledge that we have. So that is the motivation for us to do CFD. So to reiterate why we want to do this particular course and why we want to learn about computational fluid dynamics is because practical flow situations are much more complicated geometrically and physically than what we are equipped to do in our based on our knowledge given in the courses, theoretical courses that we go through. And so although there are thumb rules for designing, in practice for many of these things we cannot probe too much. For example, using thumb rules we will not be able to tackle this T junction problem and then come up with shapes of this junction which will give you 30% or 50% or 70%. If you want to do that, we have to do either experimentation, which is very costly and which is very time taking, or we have to try to solve the governing equations. But the governing equations are very complicated, in the sense you do not have a single equation, you have at least a minimum of 4 equations, and each equation is a partial differential equation. 3 of them are second order equations and one of them is a first order equation in the simplest case, and the equations are also of mixed character, like hyperbolic, parabolic, elliptic, and these kind of things, which make the solution very difficult. And so it is not the lack of knowledge of the equations, but it is the difficulty of getting an analytical solution in practical cases that makes it extremely difficult for an engineer or a scientist to tackle real world problems. But if we can do the equations, solve the equations numerically, and if we can solve the equations in the unfully developed 3-dimensional flow geometry, then we will be equipped with the tool that we can use for our design. And CFD offers that kind of tool, because CFD, a knowledge of computational fluid dynamics techniques, will enable you to go straight to the exact governing equations and then solve them in the geometries, in the irregular geometries like what we have seen, and with the kind of boundary conditions and with the kind of interventions that you want to do. So it would be possible to simulate the flow through a realistic flow equipment by going the computational fluid dynamics way, and that provides us the motivation for this course. Computational fluid dynamics is not an easy subject. It has inputs, it derives from knowledge in different disciplines, obviously in fluid mechanics, but there is also a lot of mathematics that goes with it, and there is also a lot of programming and computer science, mathematics, algorithms, and data structures. All those things will be will be needed in order to make a very potent tool, something which can be used by lots of people. But we are not going to discuss all those things in this course. We are only going to discuss the basic concepts involved in this, in the solution, numerical solution of the governing equations. So the outline, the course plan is what is given here. We are looking at a 12-week course. Within this, I'd like to take you through a CFD approach to the solution of governing equations, and I'd like to touch upon all the important concepts which will enable us to get to the solutions of these. So we have 12 weeks, including this particular week. In the first 2 weeks, we are going to look at the CFD in its simplest form. So in the first week, we are going to look at how to calculate flow in a rectangular duct. If it's a circular pipe, we already know under laminar flow conditions, okay, it will have a parabolic profile. But if it's a rectangular duct, it's not so easy. So we'll see how we can do it, how we can get the flow field in a fully developed flow through rectangular duct, using the techniques that we're going to develop further in further weeks of computational fluid dynamics. In the second week, we are not going to look at a rectangular duct, but a triangular duct, which poses additional challenges, because a rectangular duct can be described in Cartesian coordinates. A circular pipe can be described in cylindrical coordinates, but how do you describe a triangular duct? So we bring in another facet of computational fluid dynamics to deal with this. So by the end of 2 weeks, which is the first module, we have the basic idea of what CFD is, but we don't have enough knowledge to be confident about it. Okay, the concepts are still hidden. So in weeks 3 and 4, we are going to derive the equations, the exact equations which govern the fluid flow, which we need to be solving. This is not usually done in the first course of fluid mechanics. So, I am going to derive them so that we have a good understanding of what the equations are and how they come about and what is the basis for the CFD. And after that we are going to go into the third module, in which we are going to bring in the basic concepts of CFD, which will help us solve these partial differential equations. So, that is, in week 1 we are going to deal with the finite difference approximations and how we can use those things to convert partial differential equations into algebraic equations. And in the week after that we are going to look at some of the properties of this discretization and concepts like consistency, stability and convergence, which actually help us in determining what is the best way of going about this finite difference approximations to get to the solution. And in the next 2 weeks, in the fourth module, we will be looking at not just the solution of one equation, but we will be looking at the set of coupled equations which will be needed to deal with 3-dimensional flows. So, we are going to look at the compressible flow case and then the incompressible flow case. So, the compressible flow would be much more of interest to maybe civil engineers and some mechanical engineers, some chemical engineers, like that. And incompressible flows would be more for process industries, but both can be found in all kinds of applications. And the fifth module is more about mathematical techniques which are required for the solution of the linear equations, algebraic equations, which are the equations that we are really solving on computer, and we will be solving tens of thousands or millions of these equations. So, we need to be very good at solving this. So, the kind of specialized techniques that have been developed in the CFD with relation to CFD for the solution of linear algebraic equations are what we are going to do in the next 2 weeks. And in the last 2 weeks, which is the final module, we are going to go back to the finite volume method and formulate a problem, and we discuss how we can generate a grid for this and then how we can solve these things in using the finite volume method, not using the finite difference method, which is what we are going to introduce in week 5. The last week will be spent on an introduction to turbulent flows and turbulence modeling, which is required to tackle real world problems when the flow is turbulent, which is often the case in many process industries. So, we would like to be touching a bit about turbulent flows and turbulence modeling, which is required for practical cases. So, this is the essence of the course plan. Each week we will have assignments, and there will be a discussion, there can be a discussion of the assignments and other concepts in the forum, CFD online forum, and the assignments will have a deadline. You will have to submit the assignments at the end of that, and then there will be an examination which is conducted towards the end of the course. More of those details we will discuss in the next lessons. So, what we have learnt in this lesson, in the first lesson, is why we need to study CFD and why we need to go into that, because practical flow situations as shown in this figure are very different from the kind of assumptions that we need to make in order to get an analytical solution or apply thumb rules. And practical solutions require a lot of optimization, getting it correct so that we can operate efficiently. And these kind of things require the possibility of solving the exact equations correctly, and that is what is made possible using the computational fluid dynamics approach, and that is why we are studying this. Okay. Thank you. We will meet again shortly for the second lesson.